So in the last few classes, what we have been looking at is basically the various kinds of equivalent circuits for a diode. We may not use these equivalent circuits so much in circuit design, but the reason I spent some time on this is because when we do transistors, we will again use more equivalent circuits there, and it's easier to motivate the form of the equivalent circuit for the diode rather than for the transistor. For the transistor, I'll just give you that this is the equivalent circuit and we'll start. When we do transistor design, you need the equivalent circuit. You learn about how the equivalent circuit of the transistor itself comes about when you do the next course on devices. Okay, all right. So basically, we started off with an ideal diode. We started off with this ideal diode, which is basically a switch, and then we went to the real diode coming, and then we went to this constant voltage model, right? And then we went to a slightly more complicated model, which is a constant voltage plus a resistor, right? And then we looked at the small signal equivalent, okay, and we worked out what the small signal equivalent should be. Okay, in just one error the other day, people pointed out that this is not IR. This should be I times RD. Okay, there is no capital R there. Okay, that was an error. Okay, so let's start today with let's today start with some circuits. So we have finished the equivalent circuits. Now we will look at some applications. Okay. So the first one we will take. What's the first application that you would like to do for a diode? Yeah, that's the most popular one, right? So we have not done the equivalent circuit in reverse bias. We'll do that when we need to do reverse bias based circuits. Okay. So we'll start off with this idea about a rectifier, but we won't do the rectifier completely because the rectifier it deserves a complete lecture on its own. It's a very important application. Today we'll just give you a flavor of the rectifier, do some other circuits also, right? And then we'll go back and finish rectifiers in another hour. Okay. So basically, what's the application of a rectifier? What does a rectifier do? Converts AC to DC. So typically, your power supply, right? The simplest power supply that you can think of will start off with I'm sure you've done this in school itself, right? You start with a transformer. What does the transformer do? Okay, so this will be a step down transformer, right? Then the next block in power supply is the rectifier block. So basically, if I look at the waveform here is going to be sinusoid, right? The waveform of the rectifier, depending on the nature of the rectifier, right? It can either be what is called if it's a half wave rectifier, you will have a waveform like that. If it's a full wave rectifier, you will have something like that, right? What do you do after the rectifier? What do you do after the rectifier? Right? What do you want a flat DC, right? Is this a flat DC? Is this a flat DC? This is slightly more but less. It's still not DC. So what do you do? Correct. So what does that capacitor actually act as? It's a filter. right? The capacitor removes off the whatever AC component is there. Okay, so if you look at the waveform here, it will be much smoother. Okay, so I'll write like that. Okay, with some reference. Now, are you 100% sure that this voltage here, right, will be of the value that you require? Let's say you want a 5 volt supply, right? Do you think exactly 5 volts will be 5 volts or 10 volts or whatever you want? You're not 100% sure, right? Because all of these things are going to have some, when you do the filtering and all of that, all the voltage levels will change. So typically the last step in this is called as it's called a regulator. Okay, so this your typical power supply will have, even if you take a very complicated power supply, this will be the basic structure. The complication come in kind of rectifier topology, right? The kind of topology and the kind of regulator. So in fact, all of you can actually make this circuit lab, right? Once we have the plans, we will get them this week. So you can make a rectifier, right? Then you can put just a capacitor that will become your filter. Then for the regulator, you can do something. You can use, for example, reverse bias diode as a regulator. But you also have ICs that do regulation, right? So you can use those ICs, and that's what typically you would do if you want to make a good power supply for yourself. Okay? What goes into the IC, we'll hopefully do in course as time goes. Okay. So now let's start with the just rectifier. I'm going to go couple of topologies of the rectifier, and then we'll move on to other applications of the diode. Okay. So let's start the half wave rectifier. Okay, so how do you make the half wave? I have some input, right, and then I pass it through a diode, and that diode drives this is some load, right, and this is a diode. Okay, and we already have done the analysis of this one, or rather we actually plotted out the waveforms will look. How form look if my sinusoid were like that, then your waveform is going to be that. So far I am assuming it's an diode. What will happen if it's not an diode? You should put it. Okay. So I will ask you as an exercise, plot red line. Okay. So this line is plotted assuming that I diode. Okay. Your exercise is plot for a constant voltage drop model of. Okay, do that. Okay. Now, what can you say about the DC component of? Does anyone remember what the DC component of this V out is? If I call this as VP, you might have done this in school, right? Go back and check. It should be VP by pi. How will you calculate this? So this will basically integral 0 to time. So this is right? Integral of the V out of dt divided by t. Correct? Where V out is this. That's the voltage, right? So you can calculate this, and this will come out to P by pi. All right. And then what is the RMS value? What's the RMS value going to be? How much will it be? For sinusoid, what's the RMS value? 1 by root 2. Okay. So for this, it will be VP 2 root 2. Think about it. Okay. Go back and check. It will be VP by 2. Okay. Because that 2 has to come underneath, so effectively it comes out as a root. right? And so you can actually find a something called the ripple as under root of V RMS squared minus V DC squared. Okay, and you can do what's called as the ripple factor. The refractor will be V divided by VDC. Okay, this measure of how much or how bad your output voltage is as compared to DC, right? So if your voltage was exactly DC, what will the ripple be, or what will the ripple factor be? Check. 0, right? Because your VRMS will be VDC in the case of if your output were perfectly flat, right? Your ripple factor ideally will be, right? What will be the ripple factor for the half wave rectifier? Quickly calculate it. No. Put those numbers in. We did in the previous slide. Do it. It's not such a nice number. So it will, VRMS itself will be VP by VP by 2, right? VP by 2 whole square minus VDC will be by pi whole squared, whole thing divided by VP by pi. And what will this be? Under root of pi by 2 squared minus 1. You get that? What is this number? Somebody get it? So what's the number? At least estimate quickly. 1.2, right? 1.21. That's for the half wave rectifier. Okay. So the topology that will improve this, right? So we'll go to the next topology, but as you can see, I'm through this quite fast, right? We will spend a lot of time doing rectifiers, but for now let's just go through this quickly. Okay, so I'm going to go to the next one, which is the full rectifier. Using a single diode. This is the topic that you have emit for a full wave rectifier. You must have done in class, in school, right? Diodes, then people of bridge rectifier, right? So we'll come to those things, right? Bridge rectifier rings a bell. Yeah, okay. But this is just the simplest one without all of that. So the idea is the following, that you are actually starting with a transformer, correct? The secondary of the transformer is what's called center tap transformer. What's a second tap transformer? Basically, a center transformer means that you have access to the central point of secondary coil. Okay, you will do that in your machine course. So that means you can access this center point also. Okay, so what essentially it means that if I put a voltage of plus minus Vp in omega, I can get here plus minus Vp sin omega t by n, right? And here again I'll get Vp If you don't follow anything, ask me instead of discussing amongst yourself. Right? So this is an n:1 or 2:1 transformer? So 2:1 transformer, right? Because I am doing divided by n there, divided by n here, so it should be 2n. Sorry? Correct. Which one? Oh, can I explain that again? Okay, I heard that. You should be loud. So I heard that as some splitter. Okay. So basically, in a regular transformer, you have one primary winding and one secondary winding, right? And in the secondary winding, you have access to both the ends of the secondary winding. All right. Now, the secondary coil is wound on it's on a core, right? So, say at the middle of that secondary winding, you solder a third wire. So now you have 3 leads that come out from your secondary winding, right? One is the beginning of the winding, the other is the end of the winding, and you also have access to the midpoint of winding. Okay, so then will happen. Now because the flux links both the primary and the secondary, right? So you have, if I have a ratio of 2n:1, right, or basic is to half, right? So you will have half the winding here, half the winding there. Correct? So you will get this. Yes. That's what I was thinking. If it is n/1, then it will be n/2. Yeah, I think that is the correct one. Sorry. Right? So just to check, say you have one coil here, and say you have 10 here, right? So it will be a 10:2, and you will have 5 and 5. Is that right? Let's just think about that, as to what this ratio should be. Just think about that. Okay, but you get the idea. Okay? So, what do you do with this? Again, you pass it through the diode, right? And you want to put a load. So I am going to put the load here. So positive half cycle, right? I am going to take this voltage as the output. In the positive half cycle, nothing is going to change. It's going to be equal to what we did last time. In the negative half cycle, I'm going to take this, connect it there. So in the positive half cycle, what will happen? In the positive half cycle, current flowing that way, and I'll put a plus to designate that it's the positive half cycle. In the negative cycle, what will happen? How will current flow? So negative half cycle go through this, but what will be the sense of flow? Through the load? Through the load it will be the same direction, right? So it will basically go I'll use a different color for the negative half. Okay, it will basically go through that and then go back this way. Right here, drawn the wrong circuit. So it's not a diode actually. Using two. Okay. Sometimes we think more than what is actually happening. So basically, okay, I'll draw it in one way and then I'll draw the cleaner cell for the same thing. Okay. So you have that, and so you put the second diode here, right? And where should it go? Where would I want to draw this? Right? Okay, if I draw it in a way, it will become clear. Okay, the same thing can be drawn like this. And actually here you should ground this. Okay, so basically you ground this and this is your V out. Does this appear? Now is it clear? So in the positive half cycle, right, it will happen. So this is plus and again that is plus minus, right? This is, so in the positive half cycle, current will flow that way for the positive half cycle. For the negative half cycle, this load, so D1 will conduct in the positive half cycle and D2 will conduct in the negative half cycle, and current will flow that. Is that clear, Shubhangi? Clear now? Okay, if it's not clear, stop me, people. Rajat? Clear? Yes or no? Yes. Yes, good. Okay, let's see that. Now, let's take this and what is this? This is your Vp sin omega t, right? That's your input. All right. Now, in the positive half cycle, what's going to happen? In the positive cycle, in the positive half cycle, diode is going to conduct. Why? Because in the positive half cycle, this is negative with respect to this. Correct? So the anode is positive biased with respect to the cathode. Correct? So the D1 will conduct in the half cycle. What about D2? Positive half cycle, D2, this is going to be plus, this is going to be minus, right? So basically one is not going to conduct. However, in the negative half cycle, this one, D1 will not conduct because anode of D1 will be negative and the cathode is at 0. However, the bottom diode will conduct because this is negative, right? This is negative, which means whatever I have drawn as plus over here will actually be negative with respect to what I have drawn as minus here, which means this diode will conduct. Okay, this plus minus refer to input voltage. Alright. So basically, you will have a situation where the positive half cycle will come from here, and then the negative will come. And can you guess what the values of various other quantities are going to be? What do you think will VC be? 0? Who in 0? How is it 0? If it's 0, then there is no No, average only. Of the sinusoid. No, you have to take average of mod sine. And what will that be? 2 Vp by pi, right? If you didn't know that, the previous thing is Vp by pi, this is exactly going to be double of that, right? And what would Vrms be? Vrms? V by? Why? It's the same value I got for the pure side. It's going to be the same as for the sinusoid, right? Because once you square it, whether you square the sinusoid or you square this full wave rectified sinusoid, you are still going to get the same, right? So this will be P by root 2. And it would be a ripple factor. Work it out. What will be the ripple factor? The expression squared by pi 8 minus 1. What is this? Zero point? No. 0.8. Okay. So you see that this is a better supply. Half wave or full wave? Full wave. Why? Because the ripple has come down, right? From 1.2 it is down to 0.48. Physically you can actually basically you are looking at it's the RMS value of the AC component in your signal. Or it's an RMS value of the time varying component in signal. Because what have you done? VRMS is of the, this is the rectified signal, right? VRMS is the rectified signal, and then this is the D component. So you subtracted the RMS value of the DC component from the RMS value of the total signal. So what are you left with? Basically the RMS value of the AC signal. As an exercise, I want you to go and think about this. It will become clearer. We will put it, I'll put this in the also. What does it mean? Okay, just as an aside, this is an interesting problem. Let me say that I have a V, okay, V of t, which is some T naught, which is a DC quantity, okay, plus C1 some omega t plus V2 sin 2 omega t plus so forth. Okay. Find out what is, or rather prove that that the RMS is under root of V naught squared plus, what do you think this one should be? 1. So okay, to that root 2, let me make this like root 2 1 and root 2 V2, okay, so that V1 is basically the mass value. So prove that it will be this. Okay. So basically what am I saying? I am saying the RMS is equal to the, yeah, so it's the, again it's like a root mean squared. It is not very straightforward, because what is RMS? What do you define RMS? VRMS itself under of or no modulus, I can make this here, integral 0 to t V squared of t dt, whole thing divided by t, right? So when you take this whole thing, find this quantity, you will have large number of cross terms. What this is effectively telling you is that those cross terms don't appear in this. Do you get where issue is? Root of mean of squared. Root mean of the squared. Yeah, sorry. right? Everything goes under the root. Prove this. Okay. Now let's go to some other circuits. The next circuit I'm going to talk of. We'll come back to rectifiers. Okay. Design of all the components for a rectifier, the important activity that everyone should know how to do. Okay. It will also teach us how you should look at component specifications when you are trying to design a circuit. Right. You can't, when you choose your diode, can you put any diode in your rectifier circuit? It work? What kind of specification would you want on your diode? So first, in forward bias. So when you design a power supply, right? If you look at your laptop charger supply or any of those, what does it tell you? It gives you a voltage, and what does it also give you? A current, right? Tells you that you can't draw more than a certain value of current. Why is it? Why it's given? Not reverse saturation. It will damage components. So when whatever components you are choosing, right? Some resistors you are choosing, you have a transformer and you have the diodes and other things, right? Capacitor. So basically all of those components have to be chosen keeping in mind that your final circuit you are making has a certain specification. That's why you shouldn't draw more current than the specified or the rated current of that system. Correct? Many of the devices will actually have a protection so that you can't. That is the most sophisticated version of these things, right? You take your laptop charger, even if you put something and try to draw more current, it will not. It will just saturate at whatever current it's rated at. Okay, or little more. We'll see how to do that. Okay. So here and similarly for the diode. So yes, you need to know how much current you're going to actually rate your site to. That's one specification. Another specification for the cut-in voltage. Okay, that's one thing. But most diodes are around 0.7, 0.6, so not really that important. So you need the diode to be off, right? So over here, for example, you want to be on in some portion of this for some portion of time, and D2 to be off at that time. That means D2 should not break down. Basically, you should calculate what is the voltage across D2 when D1 is on, and you have to find out what is the maximum of that, and your breakage should be more than that. Correct? Otherwise, it will break down. Then you won't get a rectifier. Right? So all of these things. Now, if a capacitor, right, you want to filter this thing, you put a capacitor. So how do you choose that capacitor? Right? So all of these things go into the design of. We'll do that. Okay. That's why I want to spend time on that. What did I mention? Within the, I don't remember. Yeah, basically, whenever you're making a power supply, so your power supply will be rated for some value of current. You cannot draw more than that amount of current from the device. So that will put a restriction on. So what diode you actually choose should be able to sustain that value of current. You get some diodes which will sustain, say, 10 milliamps. Some diodes will sustain, right? Usually power diodes sustain amps. However, your small diodes will sustain only 10 milliamps, 100 milliamps. So take a 100 milliamp diode and put it in a place where you may be drawing 1 amp. What will happen? It will burn. Right? It will just burn off. So that's an important specification. Similarly, if you go back here, you would see that the operation of the circuit is dependent on the fact that for some portion of the full time period, D1 is conducting. In the other portion, D2 is conducting. When D1 is conducting, D2 is blocking. Right? So D2 should block, which means you should calculate what's the voltage across D2 when D1 is conducting, and the breakdown voltage of D2 be the magnitude of that should be much more than what's the voltage that's actually appearing. Right? So we'll calculate those things. You will see what are the advantages of this particular topology, what advantage of the other rectifier topology, and all that. Okay? All right. Okay. The next circuit we're going to do, have time. Okay. The next circuit we are going to do is called, so we'll come back to rectifiers. Meanwhile, today we will do some simple. It's very fascinating to see many things you can do with just a diode. Okay, diode, resistor, capacitor. You can do lots of stuff, right? In fact, you can also kill mosquitoes with that. We'll see how. We'll hopefully reach that stage today. Okay, so that you can kill mosquitoes with just a small 9-volt battery, 9-volt battery, diodes, and capacitors are sufficient to kill mosquitoes. Okay, those bats you have, right, which zap insects, basically that. So we'll see how that is done. Okay, so the pre-detector, let's see. I'll draw the circuit and then we'll analyze, and then you'll get a feel for how this works. Let's take this, okay, and let me feed in Vp omega t here, and that is the positive and the negative term, okay, and say that I am interested in voltage across the capacitor. Okay, what do you think will happen? Okay, I shouldn't have explained in words what it does, then it's more fun. Now you are already biased by what a peak detector can mean. Okay, so what will happen? Assume that, so this is your Vp sine omega t, okay. Initially assume the capacitor is discharged, so there is no voltage, okay. So the capacitor is at 0 this time, and in this positive half cycle, or at least till here, what will happen? The diode will conduct, correct? If the diode conducts, what will happen to the voltage of the capacitor? It will increase. And if it's an ideal diode, what will this voltage be? It will be exactly what the input is, right? Because there's no drop across the diode. So essentially, what happened? So essentially, you will go like, okay. Now what happens after this? After this, this voltage has reached Vp. The voltage is never going to hit Vp again, or at most it's going to hit Vp. So this diode will never again turn on, right? And if this capacitor is real and does not leak any charge, this diode will never again turn on. So voltage will basically always Vp. So it has detected the peak corresponding to what the input is. Okay? Yes. Okay. So start from 0. Okay. Assume that the capacitor is 0. So the voltage across the capacitor is 0. Okay? So this voltage, let me call that this. I'll call it as Vx. Okay, that's also V0 just for fun. Let's call that Vx. Let me ground this. So Vx initially is 0, right? This input voltage is higher than Vx. So this device will conducting. The diode D1 will keep conducting until Vx hits Vp, because subsequent your input voltage is going to start decreasing, and once the input starts decreasing, this diode will switch off because this voltage is already sitting at Vp. The cathode is sitting at Vp. So once the anode voltage drops below Vp, this diode cannot conduct. Okay, so that's now the same circuit. Is it that the input must be a sine? Why do that? Okay, let me say I have this some funny way. what do you think the output will be? So from here to here it will follow that, right? Then it will peak, find the peak, be there, then it will again go up, right? Then what will happen? It will go there. Okay, I have drawn it, say this peak are identical, so nothing happens. Then goes up here, hit that peak, and then remains at that value. Correct? Okay, now quick question, we'll close. Here you are getting the positive peak. What do I do to get the negative peak? Very smart. Okay, negative peak. Take that. Again, you have the capacitor. I just flip this. Okay, and take the voltage across the diode. Over here, I am not being very careful about v, small v and all of that, right? Here, we don't need to be careful. When we are doing circuits where there is a small signal and stuff like that, we will be careful. Here, you write whichever v you want. Okay, small, big, intermediate, anything is okay. Right? So, this will take the negative peak. All of you think about this. Okay? Alright. So, in the next hour, not this, at 11 o'clock, we will start with the same circuit. But instead of looking at the voltage across the diode, we will look at the voltage across the capacitor. Okay? And